Okay, so derivatives are very important because they give you rate of change of a function, and many things, requires gradients because gradients are used in optimization. They're used for some other metric you might have in the problem sensitivity, for example. Uh, so turns out that you can actually use the Taylor series expansion to figure out the derivatives. Okay, so we have I'm going to do is so we can write the Taylor series expansion of f of x, but what I'm going to do is instead of writing f of x, so we know that we can write a Taylor series expansion about x of I. So instead of writing x as x, I'm going to write it x as x I plus delta x, right? This is the same as x, just that it's a series expansion. So it's a value of x at a small neighborhood in near xi, that delta x is a small value. So we can do a Taylor series expansion of this. So note here that we got delta x. Why did that happen? Is because when we write this down, this is basically x minus xi, but x minus xi is delta x, right? Because x is x plus I plus delta x. So it's the same thing, just written differently. Okay, what I'm going to do is so let's call this equation 1. I can also write xi minus delta x as f of xi minus delta x f1 xi plus delta x squared 2 factorial f2 xi plus so on. So note that there's a negative sign here because I'm going in negative direction from xi. Okay, so with that, let's call that 2. Now I'm going to do something to estimate the derivative. I'm going to take equation 1, which I wrote down there, and trying to write an expression for the first derivative, f1 xi. So from 1, I'll move everything here and this one to the left side, and I end up with f1 xi equals f of xi plus delta x. That's the first term. It remains as it is. This f of x moves to the other side. This term moves on the other side. So minus delta x squared to factorial. Now, I also have this delta x, which I don't want. I want to eliminate. So I divide the whole thing by delta x. And so when I do that, I end up with delta x. And then this delta x square here cancels with the delta x down. So we get delta x. So now, if you remember from your class in calculus, we approximate the derivative with this term, right? F of x plus delta x minus f of x divided by delta x. That's the definition of the derivative. That actually comes from the Taylor series. In fact, this goes a step further. It actually tells you how accurate is your derivative. You know that that thing is accurate as long as delta x is very close to 0, right? That's how you get calculus, right? So it turns out that your accuracy depends on the leading term. So whatever approximation you do is accurate to delta x. So it's the truncation is of order delta x. So the way this will be written in a book would be something like this: f dash xi equals f of xi plus delta x minus f of xi divided by delta x plus O delta x. Okay, so this thing here is a new notation. It basically means that indicates terms of order delta x and more, which means that it'll have delta x square, delta x cube, and so on. So that just tells you how accurate is your calculation is going to be. If you take delta x as of order 1, say, then your error will be of the order of 1 because it's delta x. If you take 10, it'll be a lot more worse. It's be order of 10. But if you take 0.1, your error is going to be, that is, if you take delta x as 0.1, your error is going to be about 0.1. 0.01 is going to be even more accurate. So the smaller delta x is, the better is the accuracy. Okay, so this way of approximating the derivative is called as two-point forward difference approximation. Okay, so the 2-point means that you need to evaluate this function at 2 points. This one and this one, right? You need to evaluate xi plus delta x and xi. It's called forward difference because from f of xi, you look forward, you look x plus delta x. That's where the forward comes. And then the difference is obvious, it's a difference, and it's an approximation because it's only accurate to delta x. Okay. Let me write one more thing and I'll let you go. Similar to this derivation, which I did in class, you can also use. So I moved f of x to the right side and computed f dash x. There's another way of computing f dash x or f prime x. You can look at this formula, right? Using 2, you can approximate, you can find the value of f prime x using formula 2. If you do that, you will end up with a formula which looks like this. So I'll write this down and then we'll be done with today's class. So using 2, we can write f dash x I equals f of xi minus f of xi minus delta x I, sorry, delta x divided by delta x. And this is also accurate to delta x. So this thing, which I'm highlighting, is known as the 2-point backward difference formula. So we do the expression 1 minus expression 2 plus delta x minus f of equals so I subtracted those two. The first term goes away. The first term goes away. That's better. Okay, the first term goes away. The second term actually gives you f prime 2 delta x f prime of x, and the third term cancels off. So I'm just going to write the expression, but you can reason it out later on. Here is what you get: 2 delta x f prime of xi plus the second order term goes away, so we are left with 2 delta x cube 3 factorial, and then f 3 xi plus so on. Okay, so what I'm going to do is to compute f prime x, which is what you can see here. I'm just going to solve for this term. So if I solve for that, I get f1 xi equals f of xi plus delta x minus f of xi minus delta x. Then I'm going to get rid of this 2 delta x, so divide the whole thing by 2 delta x, 2 delta x. And then I'm not really interested in this term. I'm just going to ignore it. I'm going to assume that's small. But when I divide it by delta x, I get something which is of the order of delta x squared. So this is order delta x squared. Yes, so that is my formula for central difference. This is known as 2-point central difference central difference for approximation. Okay. The good thing about this particular expression is that this term, the error, is order of delta x squared. So if you compare this against backward difference, you'll see that, let's say that you choose a step size delta x as 0.1, just says that your error is going to be about 0.1, the first approximation. But because you use this better formula, it's now going to be 0.1 square for 0.01. So errors are going to be reduced for the same amount of work. The work involved in the first calculation is computing the values of f at 2 points, x and x delta x. Here you also need to do it at 2 points, x plus delta x, x minus delta x, but the errors have reduced by an order of magnitude. Okay, which just means that it's a better formula. Okay, so we've learned about 3 approximations for the first derivative. Let's see how to use that in a problem. So here is an example problem. Okay. Example: compute the first derivative of cosine x at x equals y divided by 6 or 30 degrees using 1 forward difference, 2 backward difference, 3 central difference. But there's one thing we need to also specify: the step size, the delta x. So use a step size of, well, use 1e negative 2, which actually means it's 0.01. That's the way you write 1e 10 raised to negative something, and 1e negative 4, or 0.0001. And then we'll say compare against the actual value. Okay, so very straightforward. We know how to compute the derivative of cosine x. So we'll do that first, and then see if our method of approximating it using those formulas gives us the right answer. So let's do the actual value first. Okay, so let's say that y equals cosine of x. So what's dy dx? Remember what's the derivative of cosine of x? Yeah.
Never mind. Minus sin x.
Minus sin x. Good. And so we need to find dy by dx at, so here's one way of writing it. If you want, you can write it like this, or you could write it at like this. It's really up to you. So minus sine of 30 degrees actually is 0.5. You can check it with a calculator. Okay, so this is the actual value. So now that we have a benchmark, let's compare our calculations with it. Okay, so here we go. Let's write the three formulas. We have one forward difference, which would be f of x plus delta x minus divided by delta x. Okay. So let's do backward first. And then third one, okay, so those are the formulas. What I'll do is, just to use my time wisely, I'm going to do these calculations for 0.01 for cosine of x using all three methods, and then we'll just write a program to do it for any step size, and then you can just get the answers from that. So let's use a step size of 1e negative 2 or 0.01. So 1 forward difference. So we need to do cosine of pi by 6 plus 0.01 minus cosine of pi by 6 divided by 0.01. That's my forward difference formula. Backward difference would be cosine of pi by 6 minus cosine of pi by 6 plus 0.01 divided by 0.01. And then central difference. We give some space to write the answer. Cosine of pi divided by 6 plus 0.01 minus cosine of pi divided by 6 minus 0.01 divided by 2 times 0.01. Hey, did anybody get the answer? Right. Okay, I got the same. And then I'm going to write the other one. So forward difference, I got 0.5042. And then this one I got minus 0.4956. Okay, so let's just think about the answers. So here we have three answers. Okay, the true value is 0.5, negative 0.5. Clearly, which is the most accurate one is the one right down there, 4999. Okay, it's expected to be more accurate because remember the error is of the order of 1e negative, okay, it's delta x squared. So delta x is 0.01, square of 0.01 is about 1e negative 4. So it's about accurate to 4 decimal places. And then the other one's accurate to about 2 decimal places. So 49 and 504, that overestimates and then underestimates. So what calculations we did actually make sense. Now, we need to do this for 1e negative 4. Let's just use a computer code to do that. I'm just going to be a little bit lazy. I'm just going to use ChatGPT to generate the answer. That is the code, and then just use it to verify my answers. Now I have done this calculation, so I can also verify what I have over here. So as I told you, you can actually, these are conversations in ChatGPT are saved if you choose to save them. If you don't want to save them, then you can go and do temporary chat. It won't get saved. So let's just do, let's not do temporary chat. I want to just have a series for, numerical derivatives. That way I can go back to it. So I'll say compute. So write a code, write functions to compute the first derivative using forward, backward, and central difference as a function of step size. Let's get into Python. Use Octave. Okay, so here's Octave. Okay, so this looks familiar. The formula we wrote down. Here's the backward difference. Here's central difference. Here is sort of the driver, which will call this code. What we'll do is we just take all this together and then write the necessary code, put it all together so that it generates the answer we want. Move this. My Octave is sitting right here. Okay, so editor, and let's copy these things. So forward difference. And copy. Okay. It looks well. Oh, this is Python, my bad. I shouldn't do the Python one. This is the Octave one. So copy this code. Okay, next one. Backward difference. Next one. Okay, so the way this works is that function in the end basically simplifies the function ends. So you can actually package all the functions in a single place versus writing different functions. Sometimes it's nice because then you don't have to deal with 5 files in 5 places. So it's one way of writing. The other way you could write it is you could have different functions defined as separate file. So we'll go with this flow. What you want to do is you want to have the main file which calls these functions up. So let's copy the last piece, which is this one, and then put it here. Okay, now when you define functions like this, you want to define function finite difference, and then you want to end it. Okay, so it's asking me to save this. So let me save it. Save it at desktop. Okay. Okay, now I want this to be for not x squared, but I want cosine of x. Okay. I want it at pi divided by 6, and then h should be 0.1. That's what I wanted the first time. So let's run this. So it's supposed to be for, okay, let's run, see what happens. Okay, so forward difference 5043, 4957, 500. I think it's a rounding thing. We can just try to make it format long and run this. Okay, so now it's better. So now if you see this answer against the answer I wrote down, it's not similar, right? 4999 is something which I remember clearly. The good thing about writing it this way is we can now, just using step size of 0.01. Okay. So it'll print that comment and then show all these answers. And then we need to do this all over again for a step size of h equals 0.001, no, 01. At 1e negative 4. So using a step size of, so here is, well, this is giving you the step size of 0.001. So 500049. Almost everything is very, very close to 0.5. Now, this is like one of the glitches of the software, which is it actually should have printed both the answers. It should have printed this followed by that. Let's see. Yeah, this happens sometimes. It seems like unless I comment this out, it won't print that. Anybody encounters this problem with Octave? Right, yeah. It actually works pretty well on my Mac. It's just the same code. It doesn't really work well. Well, the answers are right. It's just a display thing. If anybody gets a fix, let me know. Can I do something which will get it to print everything in one shot? So let me Control R is comment. Yeah, and it didn't even print that disk. Let's go back and see if maybe the disk is causing the problem. I don't know. Let's see. Yeah, well, that's unfortunate. That's how it works. I'll see if I can find a fix to this. It seems like you need to comment one and to get the other thing to work. By the way, this code will work perfectly fine if you take and copy paste in MATLAB. For example, in Citrix, you could do it. I don't know if there's an on. Has anybody tried an online Octave? There is a version which you can use online Octave. So there is this tool which you could use, but I don't know if you can use, right? So I want to use the screen. Okay, looks like you need to sign in and then you can write Octave code and run it. You could try this too. Maybe it works a little better. Okay, so I think the answers are right, just that you need to play with it to get the answers, unfortunately. I'll see if I can find a fix to this. It's like a display issue. Any questions? So this was the second part, gave you the answer for 1e negative 4, which you should copy on in your notes. Let's move on to other things. Okay, let me just write the solution here, so that way you have it when you try it out at home using Octave for delta x is 1e negative 4. We get the following: forward difference, backward, and central. The answers I got were minus 0.50004 minus 0.5949995 minus 0.49999. Okay. Okay, so this is how we've got an approximation for f of x, f1 of x. But sometimes we're interested in other things, like how do you approximate? How do you get the derivative of f2? So the second derivative of f and third derivative of f and so on. So you can actually derive a formula for the second derivative of f by doing the following. So one can use the Taylor series to get f2x, f3x, and so on. Okay, so just like I manipulated the equations for the f of x plus delta x, f of x minus delta x to get f dash f1x using forward central, you could do the same thing for the second derivative, third derivative, because all those derivatives are available in that expression. So example is if you, and here's an example of f2x computed that way. What I did was I added 1 and 2. Add 1 and 2 and solve for f2x. So if you look at these expressions, if you add the first and second expression, okay, so if you add these two, then you'll see that this term will cancel with this term, right? Because it's plus and minus. So when that cancels off, you will be able to compute the value for f2x, right? So that's pretty much what what I'm trying to do here. So doing that, you can solve for f2x, and it comes out to be f of xi plus delta x plus f of xi minus delta x minus 2 f of xi divided by delta x squared. And it also gives you a truncation error of delta x squared. That is, this is only accurate to the order of delta x squared. So if 0.1 is your delta x, then it's only accurate to 1e negative 2 or 0.01. Okay, so this one is known as, it's 3-point second difference approximation. 3-point because it needs 3 points, x plus delta x, x minus delta x, and x. And then its second difference gives you f2 of x. Okay, so there's a forward, there's a backward, and so on. And there's no point in trying to derive and trying to see how to manipulate. I'm just going to give you this. Well, you can see the notes. The book has derived expressions for forward difference, central difference, backward difference, for first, second, third derivative, and so on. And they have different orders of approximation. They have different errors. I'm just going to give this to you, and we'll just use it from the table. So here is an example of computing using forward difference approximation. This is only accurate to delta x, right? So first derivative, second derivative, third derivative, fourth derivative. Okay. If you want a better approximation, delta x square, you want to use these expressions. Okay. So what you notice is that if you want to get a lower order error, if you want an error of delta x, you can actually live with, well, for f1, just two computations, two function evaluations. For f, the second derivative, you just need three evaluations, fi plus 2, fi, fi. By the way, this f of I means, put it here, f here, f of I means f of xi, and f of I plus 1 means f of xi plus delta x, and then f of I minus 1 means f of xi minus delta x, right? And then if you have I plus 2 means xi plus 2 delta x and so on. So this is, maybe I should, let me just put it down here. I think you'll forget. So let's take this. I'll write one more down so you get the hang of it. If you have f of I minus 2, it will be f of xi minus 2 delta x and so on.
Sorry, I'm going to put this in my back. I'm very sorry.
Okay. Okay, so as I said, for this one, you need two function evaluations. If you want to go for a better accuracy, delta x square, for the same calculation, you need to do now three evaluations, function evaluations. You need to do more computations. Let us look at this one. You have to do, you want to compute the fourth derivative using of the order of accuracy of delta x. You need to do 1, 2, 3, 4, 5. But here to get the same higher accuracy for the fourth derivative, you need to do 1, 2, 3, 4, 5, 6, right? Now, you might say, what's the big deal? You know, I can easily do that calculation. So if it's like cosine of x, sine of x, it's very easy. But sometimes when you are solving a real world problem, let's say you want to do finite element calculations, those calculations sometimes require you to do a series of calculations to get f of I, in which case the terminology used is that the function evaluations are very expensive. Then you might not want to use so many terms, 6 terms. You might just live with 4 terms. An example is, if some of you are working on the undergraduate research on human experiments where they make a person move, and when the person is moving, they're trying to estimate how things are going. So they want to estimate derivatives. So every experiment involves a person to walk, in which case, the function evaluations means you need to make a person do an activity for X number of minutes. So that evaluation is now going to take you, 5 minutes. So if you do 5 computations, it's going to be 5 times 5, 25. But if you use 6, it'll be 30 minutes. Sometimes there's a difference between going 24 versus 30 minutes, in which case you might want to do short number evaluations. And that's why it's important to know the trade-offs, the trade-off of number of function evaluations versus the accuracy which you get from doing those calculations. Okay, so that's the forward difference. You get a backward difference, which is similar types of formulas. Okay, you clearly don't want to, you want to just not memorize it, but when you do it for the exam, you want to write these formulas down so that you have the access to them. Just sub in those formulas and you'll be able to solve the problem. You could also get Octave, ChatGPT to write the code for you if you're trying to solve this problem. So central difference, okay. Here you'll see something interesting. So for forward difference and backward difference, we only had delta x and delta x square accuracy, but for central difference, by default, we get a delta x squared accuracy and delta x is to 4. So very accurate, but you'll see lots of function evaluations. Okay.
Question.
Yes.
Why can't we just, instead of using the less error ones, why can't we just use a smaller delta?
You can use smaller delta x. So what happens is when you use a very small delta x, there is something called what do you call that? It's called round off error. So the calculus says that the approximation for f dash x, f of x plus delta x minus f of x divided by delta x as delta x tends to 0. So the question is clearly, can you make delta x to go to arbitrarily close to 0 value? If you go very small, let's say 1e negative 5, you're fine. If you go 1e negative 10, you might also be fine. But once you hit starting 1e negative 12, your computer is only accurate to 13 decimal places, which means that when you do that perturbation, your values will only be accurate to 13 places. So you will end up subtracting, you'll end up eventually doing 0 minus 0 or value, same value minus 0. You can try it out. So there is a trade-off between that. You cannot just go very low in terms of delta x. Actually, there's a formula which is if your accuracy is 1e12, then you need to do square root of 1e12 to use for finite difference. There's an optimum value of for delta x. It's really square root of the machine accuracy. That's a very good question. Any other questions? Okay, so I'm going to write a problem down and I'll write the solution, but I would just expect you to do it yourself because I sort of laid down the everything you need to know in order to do these calculations. So compute this. So here's another example with higher order terms. Second derivative of tan of x at x equals y divided by 6 using 1 3-point central difference. And I'll just specify the accuracy because there are a number of ways. There are two ways, at least two ways in the formula sheets. So let's go delta x square. 3-point forward difference. And use a accuracy of delta x. So 3-point backward difference. And use the formula for truncation error delta x. So use step size of 10 raised to negative 2 or 1e negative 2 and 10 raised to negative 4 or 1e negative 4. Okay, and of course, compare against actual values. So let's do the easier part first, which is the actual value. It's super easy to calculate once you know the derivative. So solution is to the actual value. So we have y equals tangent of x, f1 of x, or let's just write it as f of x. The derivative of tan of x is secant square x. And then if you want to compute the second derivative, you'll have to use, the chain rule. So secant square x will be 2 secant of x. And then you take the derivative of secant of x, which is secant of x and times tangent of x. So the answer is 2 secant square x times 10 of x. Okay, so evaluating f double dash at x equals pi divided by 6, which just means you need to sub in the formula, the value for x, you get 1.5396. So that's our benchmark value. We need to now compare it against the formulas. So let's go through these formulas from the table, and then I'll leave the calculation to you, but let's just identify which formulas should we use. Okay, so let's look at the first one. 3-point central difference delta x squared. So let's look at the table for central difference. We want delta x squared, so it's here. Second derivative is here, and it's 3-point, right? This is the formula. So this is the first one. Okay, the second one, 3-point forward difference delta x. The forward difference delta x is here. Second derivative, this is the one. So this is the second one. And then third one, let's pick. So backward difference of order delta x. So backward difference is here. Delta x is here. Second derivative is here. So we need to use this.